name's Gilad Bracha, and I work for Google, and I'm here to tell you about Dart, which I'm sort of hoping you've already heard something about. Good, bad, indifferent, at least something. And so Dart is a new programming language that we're working on at Google. And we're doing this because we think web programming is in desperate need of improvement. We do a modest amount of such programming at Google, and we find that present methods are costing us a lot and are rather difficult. And so we embarked on the Dart programming language project to help improve that situation. Now, obviously, there's more to it than just programming language. There's tools, there's platform, there's libraries, there's all kinds of things. But whatever it is, language is fairly central to it. And so we want to create a language that supports what I'd call civilized programming on the web. And if you wish to infer anything about the current state and its civilization, you're welcome to do so. Basically, Dart is there to make it possible to do web applications that are as good or better than native applications with as comparable effort, hopefully less effort. Current state of affairs, people do interesting web applications, but it's fairly heroic, and it should not be heroic. And so we're trying to create something that basically makes it easy and straightforward in a way that's comparable. I mean, great applications are never easy, but jumping through insane hoops is not what you should be doing. You should at least have a tool that is approximately designed for the purpose you're using it for. And so Dart is a language that is not trying to really radically change the state of technology in theory. It's trying to provide you with something that's workable in practice. So you'll find that it's rather a familiar-looking language. It's designed so that most mainstream developers will not go into shock seeing it, even though I'd argue that if we had something that put them into shock, it would probably be even better. But I'm sort of in a minority from that point of view. So yeah, class-based, as you'd expect. And so here's a little piece of Dart code. As you can see, it isn't very hard to read. We've got a class point. It has two instance variables, x and y. It has a constructor. There's a bit of sugar there for the very common situation where all the constructor is really doing is taking its parameters and assigning it to the corresponding instance variables. People do that enough so that there's a little bit of sugar there. We're trying to make things convenient and cut on boilerplate without going overboard on the syntactic sugar, which is always an issue, right? Every piece of syntactic sugar you give people results in requests for more syntactic sugar, and it's a judgment call as to how far to go. But this should be fairly clear. And then we have a method. The method is named plus, and it takes something and extracts an x value from it, adds it to the current point's x value, gets its y value similarly. Presumably this is a point, but it really doesn't have to be. It could be anything that has an x and a y, right? And produces a new point. So it basically is a method for adding points. In short, you can look at this and you can get the idea that this is not going to be something that will be very hard for you to read and understand as it stands. But obviously there's more to that. So the other thing is Dart is an object-oriented language, which most languages widely used today are, but it's a purely object-oriented language. That means that everything's an object, which of course has many precedents, and some that are fairly widely used today and some that are catching on. And that has lots of advantages. Generally, having a uniform model makes things easier for everybody, for the programmer, and believe it or not, it's actually making it easier for the implementers. Dart is run by my good friend Lars Bach, who is the guy who did V8. He's the guy who did Hotspot in Java. He's responsible for much of the high-speed virtual machines that the world is using today. And so there's certainly an interest in making this perform well, and there's a lot of expertise on doing that. And having this pure model is actually a plus. So in particular, there's no auto-boxing going on. There are no hidden coercions. That's a huge problem in JavaScript, by the way, in general, is the fact that things get coerced in different ways, and there are these extreme examples where true becomes false, and array is turned into strings, and all these kind of things. And that's a lesson that most of the world learned, I'd say 45 years ago, right? In the 60s, basically, there were a lot of languages that did a lot of implicit coercions, because when you think about it, briefly, it seems, oh, yeah, that's a good idea. It'll just convert it to whatever I meant. The experience was that this was an unmitigated disaster, and yet we're back where we were in 1968 or so. So Dart doesn't do that. Everything's an object. Nothing ever gets coerced by itself. Nothing happens automagically in that way, and rarely needs to be. So things are a lot more predictable and easy to use. Another interesting property, Dart is optionally typed. So what does that mean? You're going to hear more of that term optionally typed all over because we're not the only ones doing it, it turns out. So optionally typed, here's our class point again, but something's happened to it. If you look, shows yellow. I used to use red, but I learned that projectors don't like red. We have here types on the instance variables, so we know they're integers. We know that the operator takes a point and returns a point, the plus operator. So what does that do? It basically makes it easier to read. It's a form of documentation. That's the main interest here. It's not necessarily about error checking, though it does do that as well. But it's mainly documentation for you, the programmer, and for the machine, for the tooling. In particular, this program will run just like the other one does, and all kinds of intermediate states will run too. You don't have to pass the type checker in order to run a Dart program. That's very different from, you might look at this and think this is vaguely Java code, but the idea here of optional typing is that typing is truly optional. It's the type checker in your service rather than the other way around. And that's an approach that, has elicited a bit of controversy, but we very strongly believe in it. So what this program will do is exactly, what this code does is exactly what the code I showed you before without the types. The types do not change behavior, ever. They do not introduce hidden casts or coercions. They do not affect overloading and which choice of method to use. They have no semantic effect. They're there primarily so that the code is more toolable, that you, the programmer, can read it and understand it better. And, if the implementation can ever figure out anything more that it could use this for, it can, but it has to preserve the semantics. It can't change what the code does. And this is very different from the type systems used in something like Java. So I've spent whole talks talking about this, but this talk I'm kind of bored with that, so we're going to give this quick intro of the highlights of Dart and then delve deeper into a few issues that we're developing with an eye toward the future. So, beyond optional typing, single inheritance. Well, that's not a huge surprise. Multiple inheritance is another one of those things like coercions that got discredited a long time ago. Has some advantages, though, but overall, people found that it's much more predictable and easy to deal with when every class has a single superclass. So that's not very radical and shouldn't surprise anyone. However, there are times when this is a problem, which is why we're actually going to move to mixin-based inheritance. I'm not sure if everybody here knows what that is, but that's why a good section of the talk will be spent explaining what that is. It's basically a way of keeping the simplicity of single inheritance both in the runtime and in the structure, but letting you share code and reuse it a little bit more. What else can we say in terms of buzzwords about Dart? Message-based concurrency, right? So Dart uses an actor-like model. We call them isolates. They're things with independent heaps and stacks, and they communicate via message passing. So you never have shared state concurrency, you never have locks, you never have deadlocks, you never, all the good stuff that you know and love from the Java world, perhaps. So that's basically, nothing here is particularly radical, but it's a good combination. Finally, mirror-based reflection. I'm going to spend some time on that toward the end of the talk. Reflection is what makes languages dynamic, right? It's not the languages that are really dynamic. If you want to, all languages are dynamic in the sense that they evolve over time. What is dynamic are the programs you write in the language, right? In a dynamic language, you can change, that program can itself change itself over time and do interesting things and adapt. And that's something that we want to have. At the same time, we need to control this for purposes of performance, for purposes of security. And so we need a more structured approach. That's mirror-based reflection. I'll talk a fair amount about this as we go on. So in terms of what kind of beast this is in reality, we have two main implementations of Dart. we have a compiler that compiles to JavaScript, and we have a virtual machine. And the virtual machine is a lot nicer because there we can actually take advantage of the underlying real machine, which has better primitives for getting the right semantics. Getting the right semantics on top of JavaScript is really a challenge because basically the language often doesn't have the primitives you want, and it tends to enforce, you know, its point of view on anything that's running on top of that unless you do a really thorough job of analyzing, and a lot of hard compiler work goes into making this behave properly on top of JavaScript. But that's crucial because JavaScript is everywhere. JavaScript is in all the browsers, and while we definitely would like to see Dart VMs in browsers over time, we don't expect that to happen overnight. And so it's crucial that, you know, you can convert it to JavaScript, run it on any modern browser, and so there's no barrier to deployment and use of Dart from that perspective. So on the other hand, the virtual machine is also useful for a couple of things even now. One is, of course, on the server. You can get better performance. Some features will just work better. And you can also take advantage of it. In fact, generally people do during development. Because one of the problems with tools that compile to JavaScript is that because compiling to JavaScript is a non-trivial task, they tend to take a fair amount of time if they're doing anything interesting. If their semantics deviate in any serious way from JavaScript and try to solve some of the problems you have in JavaScript, then it turns out that you sit there waiting for a compiler, and you don't want to do that. The advantage of having the Dart VM is that we can actually give you a development environment with instant turnaround using the VM. And then you take that same program, you press a button and choose to run it in JavaScript and see that, you know, it runs either way. And you can develop in the browser with the Dart VM because our development environment comes with a version of Chrome that's been retrofitted so that it contains a Dart VM. And so you can actually test your working web programs, a display HTML, all of that with instant turnaround using Dart without going through a long compile cycle. Anyway, I hope that the world will eventually become a better place, and we'll have Dart engines in a lot of places, but that's going to take time, and we're not letting it hold us up at the moment. So this is just a picture of that same thing. Basically, you can take Dart code and either feed it into a Dart VM or via Dart2JS, our Dart to JavaScript compiler, feed it into JavaScript. And Dart2JS is a pretty serious beast. It's already the third generation of this compiler that's been developed in, I guess, the past year and a half or so. And it gives you performance that's very, very similar to native JavaScript. The goal is essentially 100% of not to lose any performance in compilation. It gives you reasonably small downloads because it does tree shaking inherently during the compilation process. And puts out relatively readable JavaScript, though I really think that as we move forward, that'll be less of an interesting concern. So that's kind of just a very short overview of Dart in, you know, a few minutes. And beyond that, I want to talk about some of the things that we haven't talked about in talks before. There are a lot of overviews of Dart you can get. If you search YouTube, you'll find me and others expounding on this in great detail. If you want more nuts and bolts stuff, you can go to our website where we just announced our M1 release, which is a milestone 1. That's sort of something, I don't know, somewhere between an alpha and a beta. But it means that we're going to try and steer away from breaking language changes at this point. And there's videos, there's tutorials, there's all kinds of stuff, right? So I'm not going to spend a lot of my time going over that ground again. Instead, I'll talk about some of the interesting things that are happening after the M1 release that will make Dart a better language still. So one of them is mix-ins, which aren't there yet, but they're going to be in a future milestone at some point before this becomes a product. We haven't actually finalized the design, though we do have a pretty good idea what it'll look like. Small matter of implementation, but at Google we have people who are good at that sort of thing, so I don't expect to see many problems. We have done mix-in based languages before many times, and so it shouldn't be a radical surprise. Now, I'm not sure everybody here actually knows what a mix-in is, so I'm going to show you. Here's our old friend Point again. Now this stuff, the stuff in yellow bold, right, that is literally a mix-in. That's the thing that follows the class declaration between curly braces. That's the stuff that the class is adding to its superclass, right? That's the delta, the difference between that and the superclass. That's really what a mix-in is. It's what is getting added. And you know, syntactically, you can see it in this picture. And the point of this is that if you could separate that, you could attach that to multiple class hierarchies. And that can be a really useful thing. So if we want to look at a classical example of mix-in use, here is a collection class. Well, it isn't really a collection class because it won't fit on a slide. But it is, shall we say, an extended subset of Dart's collection class, right? And the mix-in, again, will be the stuff in yellow. So in particular, the only interesting thing here is this map function. It's a classical function on collections, right? You give it a function, it applies the function to all the elements in the collection and gives you a new collection back with the results, right? Basic building block of functional programming, of object-oriented programming as well. It's been around in object-oriented programs since Smalltalk, 76 or so probably. So it's been around for 36 years. And the problem is that not everything can sit in the collection hierarchy. There are a lot of collection-like things. It's a very useful interface. And these pieces of implementation are very generic and independent of for the most part, of representation. And you'd like to use them in other hierarchies. Classical example are GUIs or, for example, the DOM. So the DOM has a bunch of stuff that needs to look like a collection and behave like a collection in our library. And one way you could do it, basically, with the mix-in feature is basically mix in collections. Because the problem with these DOM classes is, of course, that they have to be part of the DOM hierarchy. And with single inheritance, they can't be part of the DOM hierarchy and the collection hierarchy at the same time. So what are you going to do? You don't want to do real multiple inheritance, because then you run into a lot of nasty questions of precedence and conflicts between methods and things like that. What mix-in-based inheritance basically preserves a single inheritance chain, but it interjects the functionality of a mix-in along the chain. So you still have a single inheritance chain going in one path up from your class all the way up to object. But you get more functionality in there. And that's how you can actually avoid replicating this code in multiple places, because that's obviously a bad thing, because then when you maintain it, you have to change it. Any bug fix, if you copy the code, that's a problem. If you add stuff to collection, that's a problem. More stuff you have to copy and so forth. Of course, if it was just this one, it wouldn't be that worthwhile adding a language construct, but of course there are others. And in fact, there are about 30 of them. I know because I put that map thing into our collection library and discovered to my horror how this was set up. So obviously we need to solve that in a more elegant fashion, and that's one of the things. This is a poster child for mix-ins. It's one of the things we're going to do. We have quite a few other uses in mind in the library, and so we expect our libraries to change a fair amount once mix-ins come in. So some caveats in fine print. We'll probably do this in stages. The initial mix-ins will probably have restrictions about using fields and all kinds of other stuff, and we will gradually move this in bit by bit. But ultimately, our goal is exactly what I showed you. Anything that's in the delta of the class, we expect to be able to represent via mix-in and share without replicating. And I think this is a good opportunity to just give people a bit of background, because nowadays people tend to forget where ideas come from. Eventually we end up in ridiculous patent wars as well over stuff that was all invented many years ago. So mix-ins originated in Lisp, in the object-oriented dialects of Lisp. It was more or less an idiom that took advantage of certain ways they were doing things. Eventually, it was recognized as a language construct. I wrote a paper a long, long time ago with William Cook, who's now a professor at UT Austin. And if you really want to delve, deep dive into this, it's still out there and still gets cited. We implemented this again many years ago in a Smalltalk dialect that Lars and I and a few others worked on, called Strongtalk. That implementation was the first time this was actually put into a virtual machine. In fact, it's the only time it's really been put into a virtual machine. All the implementations you see today are doing sort of code copying under the covers, and that's kind of unfortunate and wasteful. Eventually, we'll probably get the Dart VM to do something similar to what we did in Strongtalk, so that there's no space overhead to this either. You may have heard of things like traits. That's sort of a lobotomized version of mixins, with again restrictions on state and so forth, that has gained some popularity in some languages. You can see a variance of this idea in Ruby, in Scala, and Newspeak in other languages. So it's not actually a radically new idea, but it's only starting to hit mainstream, I think, at this point. Next, I want to talk a little bit about isolates, asynchrony, concurrency, and so forth. As I said, we don't do shared state concurrency, partly because it's evil and partly because we're running on the web and we have to compile the JavaScript, so we really can't. So that helps keeps us honest. You build your programs out of isolates. They're sort of actor-like things. Hopefully everybody knows what an actor is, but ultimately this is an entity with its own logically thread of control, its own heap, its own stack, and you can't share anything except by sending messages and copying things essentially between these things. It's a bit like, for example, Erlang, but it's also different, right? These things don't block. They're closer actually to the original actor model as proposed back in 1972 by Carl Hewitt, right? That's amazing. I mean, people were still programming with abacuses back then, but we're only now, 40 years later, starting to see this idea really getting into real applications. So isolates communicate through ports. Again, this is a low-level plumbing mechanism that lets you send messages to a port, and the receiving isolate has a receiver port where it gets the messages off of, acts on it, and may choose to reply, etc. So in a way, this should be familiar to a lot of people working with Scala or in the JavaScript world, Node.js. When you send these messages, you get a future back, and the future is essentially a promise that eventually some result will be there. It's all asynchronous because this is a completely different isolate, and you can set callbacks on those futures and have code execute when they're actually ready. So this again is not all that radical, but having it put into the infrastructure from day one helps, and we intend to make that nicer and raise the level of abstraction. The exact way we do that we haven't decided, because what's very clear is that Node.js, that model is far from perfect. What you end up getting is a lot of nesting of these callbacks on futures, and then you callbacks on the resulting thing and so forth, and it gets a little hard to work with. It beats threads though. It beats shared state and all the horrible bugs you can get there, but it still gets rather tedious fairly fast. So if you look at this is a very, very simple example. Again, something I can fit on a slide. Assume you've got these two sources of data that you call asynchronously, and you intend to plot them. So one you're going to get a list of points from one server and for the x-axis and a list of points for the y-axis. And to do this, you're actually getting a future back, and then you have to set an exception handler on the future, and then you have to wait on the future with a callback, and when that callback resolves, you have to see if the other future arrived. And future libraries can make this easier, right? You can have abstractions that manage both of these at once. But even here, right, the nesting, it just syntactically doesn't look good because these closures inside parameter lists, etc., the parentheses kind of multiply. It gets tedious. And in real code, it can get a lot worse. So is there anything we can do about that? Well, we think we can. We're still thinking about this. This, again, this is even less, this is more speculative than the mix-in stuff I talked about, because we still haven't decided on a plan on what constructs we want to introduce. But we're looking at this because we really feel that it's important to address this issue and raise the level of abstraction there. So possibilities. C# has this thing called await. That involves, that's popular, that's kind of nice in a lot of ways because it lets you pretend that you're writing sequential code. That's also bad because it lets you pretend that you're writing sequential code and it isn't. And one of the problem with these kind of illusions is that they work great until they stop working, and then it gets nasty. It's also a very complicated transformation, so we don't know if we really want to go in that direction. Compromise is a thing we're looking at called async blocks, which is a more restricted form of this. If you know functional programming, you could think of them as future comprehensions. If you don't, just ignore that. The advantage of that is the transformation is very local, and you have a much better handle on what you're getting. Promise pipelining is a mechanism where the futures still accept the method calls. So you get a future and you keep acting on it. They just keep piling up futures for their results until something is actually ready. This works nicely until you actually have control flow or I/O or something where you actually really need the result. And so it's not clear how well this is going to work for us in a language like Dart, which doesn't have first-class control constructs. So these are kind of things we're looking at. Here's again, this example is too simple to really show off the advantage, but this is one of the ideas of the async block that we're talking about, where you send off these two tasks in parallel, and then inside the async block, it'll serialize them, it'll wait for the results essentially, and do its thing, and you can set an exception handler very easily on the whole thing, right? And in larger examples, this tends to pay off more. We've looked at, for example, how the Dart to JS compiler, which is tens of thousands of lines of Dart code, which is opening multiple files and compiling them and sending off asynchronous jobs to do that. And it looks like this might help. On the other hand, maybe better future libraries will help enough. This is just to give you an idea of the sort of things we're looking at, and the fact that we're attuned to this and we're worrying about it. The other thing is that this thing works through ports, right? So you send essentially serialized data on ports. You send these messages. And that, again, it's like JSON or things like that, lists of primitive values and things like that. It's not necessarily the most attractive way to do things. And it would be much better to view these actors, these isolates, as objects that you basically send asynchronous method calls on. And you can do that fairly easily. This is, again, an outline of how you can do it. We have someone who's actually working on a more realistic version of this. But basically here we have a isolate wrapper class. The idea is you send it a port to some isolate you want to communicate with when you create it. That's what the constructor is doing. All right, where you see isolate wrapper, it takes this .send port, so it's basically getting a port and setting its send port field. The underbar indicates that it's private, a convention we got somewhere from Python, but that we actually enforce in our libraries. And what it does is it gives you the object has a no such method. So no such method is there are similar constructs in Smalltalk and Ruby. Basically, it's a handler for what happens when your object doesn't have the method that was invoked on it, right? Rather than just dying as a Java object does, you can set a handler that will try to do something intelligent. It basically gets information about the call, the name and the arguments. It's going to be a little more elaborate because we have optional arguments and named arguments and things, but basically, you get this information and you can decide what to do with it. In our case, we simply want to send it over the wire to the port, right? And the port will give us a future back, and that's what we want to, the call on the port will give us a future, and we want to return that. So with this, we now have an object that essentially responds, to any message, you send it something with a message, and it will encode it, pass it to an isolate. Presumably the other side of this equation is something that picks up that message, translate it, and uses reflection to invoke the appropriate method on the isolate, give you a result back eventually, and so you work with objects rather than worrying about lists of stuff and so forth. So it's relatively easy to do that. No such method is a really handy thing that's missing in things like Java, missing in JavaScript, though you can with some pains emulate it. That's what our Dart to JS compiler does, for example. But it's nice to not have to worry about this and have a standard way of doing this thing. So that is, concludes our whirlwind, show of isolates. And the rest of the talk, I really wanted to talk about mirrors because that's one of the things I really care about. So mirror-based reflection, again, has a significant history. originated in a language called Self, where a lot of other things originated, including the kind of modern JITs that we see in things like Hotspot. Basically, the technology that makes all these languages fast, right, comes from there. Used it. The first class-based language to use it was, again, Strongtalk, which is a Smalltalk dialect we worked on. Eventually, in Java core reflection does not use mirrors. Java core reflection uses, the more classic approach, which I'll talk about in a moment. But the Java debugging interface, JDI, does use a mirror-based approach, as does the annotation processing toolkit, right? And they do that because the classic approach just breaks down. And of course, you see it now. Scala now has a mirror framework. Just came out probably 6 months ago or so. Other languages. And we're doing the same in Dart. Now again, caveats, this is work in progress. We don't have all of this stuff yet. Dart2JS doesn't do this yet. The VM does, but you can't really bank on that in the sense that if you wrote an application using it in the VM, you won't be able to deploy it to JavaScript because that's still not there. But it should be over time. And again, the APIs, the details may change. So this is more of a preview. But it does actually, unlike the other things I've talked about as future plans, this is already in progress, and I'll be able to demo some of this for you in a moment. So just to make clear what the difference is. So classic object-oriented reflection, as, say, in Java, and of course it doesn't originate in Java, almost nothing does. It originates in Smalltalk and was then picked up by the Lisp people and CLOS and so forth. But all these languages have a very, very plausible approach to this, which is to say, I've got an object. If I allow you to get at its class, the class is a natural clearinghouse for all these reflective queries, because really this is where the data about, all this stuff is, that it keeps the representation, it knows about what fields I have, what classes I have, etc. It's a natural place. And this is an approach that people have taken throughout the history of dynamic languages, because the easiest thing to do, and in some ways the simplest and most elegant, is simply to expose your data structures to the programmer. That's what happens. Your interpreter or whatever structure you have in an OO language you have a class, you simply throw that out to the programmer and say, here, mess with it. You'll be able to do wondrous things. There's only a slight downside to this, which is that they'll also be able to do horrible things. And the question is, how do you balance this? So mirrors are a way of balancing it. Mirrors, as you can imagine, are objects that reflect other objects. If you don't believe me, check out your bathroom. And the beauty of that is, like, every problem can be solved with a level of indirection. And mirrors give you a level of indirection because now I can control who gets what mirror, right? It's a separate object. Before I had an object, obviously I could call getClass on it. The whole reflective thing was there. And there was no good way to control access to it. Whereas here, I actually can tell, are you going to get a mirror? If you don't get a mirror, I can make your program about as dead as a Fortran program, right? As completely non-reflective. And that means I can deploy stuff without reflection if I want to, because I'm short of space or I'm short of bandwidth, which is what happens on the web, right? In embedded situations, it's more about the size of the thing you're doing. In the web scenario, it's about the size of the thing you're downloading initially and things like that. So that helps deployment. Also helps security, because obviously I can give you mirrors that won't do bad stuff. I can give you mirrors that only let you reflect on yourself, and I can give you mirrors that will not let you reflect on something else. There's all kinds of potential mechanisms to solve this. Works well with distribution as well. That was really the problem, for example, with Java reflection, right? Because they found, well, they were multi-threaded, and they found that, writing a debugger using reflection, which was one of the initial use cases, fell flat on its face because everything started to deadlock because they were all in the same process. And so when they decided to do out-of-process debugging, there was this problem that the core reflection framework in Java just couldn't do that because you needed these magical class objects that were only in that VM. So you eventually go to mirrors or separate objects, and you can give different mirror implementations, like proxies and stuff like that. So it solves a whole slew of issues. And that's why more and more languages are using that framework. And in Dart in particular, we want the mirrors to allow you to reflect between isolates, right? So you would be able to actually propose reflective queries to another isolate, which means that the API is in some places asynchronous, which means that it, in some places, is a bit harder to use than it might otherwise be. We're trying to preserve that property because it does have the nice thing that anything reflective you write would actually work in the distributed scenario. On the other hand, we are trying to structure it so that we minimize asynchrony, so we don't, asynchrony, so we don't burden you with this stuff all the time. So we're going to look at this briefly because we should actually show you some real live code. So this is the Dart editor. Can people in the back see this? Or we can still kind of zoom a little bit in. Right, and we have this little program. Dart programs can be structured into libraries. You don't necessarily need to declare a library. Essentially, you can write a script without a library declaration. Dart is designed so that you can get into it gradually and you don't have to put up a lot of boilerplate, to get started. But on the other hand, when you're writing, substantial code, software engineering becomes important, so we do have support for that. So here we have this little library that's just I set up for a demo. And the important part is that we're importing the mirrors library from the Dart core library. If we actually zoom out, we can see over here, this is Dart mirrors right here. This is the core library with all kinds of stuff in it, HTML, for the web, I/O, isolates, JSON support, math, etc., etc. We also have mirrors, which is still a work in progress. So we're importing this thing. And that'll let us use the functionality of mirrors, obviously, in the scope of this little application. And we have, again, a class point, slightly different, a very, very basic class point with two fields that are just set to 0. Now, we have this method, print fields of object. And what this method does is you give it an object, and it's going to print out the values of the fields. Basic introspection. This is next to nothing. You can even do this in Java. So we're not using anything heavy duty yet. The way you do it, however, with mirrors is a bit different. So reflectism is a top-level function that comes from the mirrors library, right? And you give it an object, and it gives you a mirror on that object, an instance mirror. An instance mirror is a mirror on a particular object. We have all kinds of mirrors. We have class mirrors for looking at classes. We have library mirrors for looking at libraries, method mirrors, etc., for various purposes. We get an instance mirror on this object. Now we can get the class mirror out of that, right, by doing essentially om.type. So type is an accessor on instance mirrors, and that'll give us a class mirror. Now that we have a class mirror, we can go over this information and loop over it in a for loop and extract the variables, right? The class mirror has a method variables that'll give us a map of names to variables. So it'll basically be something we can look up the name of any field in this class and get a variable mirror on it. Calling get values, we get a list of those variable mirrors back, and that's what we're iterating over in this for loop. And with every one of these, we're going to extract its name. We're going to use that name to get the value of the field out of the original object. So we got the names out of the class mirror. And now we go back to the object mirror that we started with, call get field with a field name, and that's going to give us the value back. Actually, because it's asynchronous, it's going to give us a future for that value. And that's important because we might be looking at a different isolate, in which case, there's no reason to believe that it's going to stop everything it's doing and pay attention to us. It's not supposed to do that. It just got a message requesting this, which is somewhere in the message queue, so obviously we're not going to get the result right away. We're going to get a future. We then set a callback on that says, well, when that future is ready, then we're going to get v, the actual value, and we're going to print that with a field name and the value v, right? And notice we didn't have to do this asynchronous stuff on the other things because basically the thing is designed to pull up all this reflective information on a class. Once you ask for a mirror on an object, it'll get you the reflective information for its source base so that you don't have to go every step of the way and keep asking for futures and things like that. So once you've done that, we should be able to actually run this thing. So we have a main function. Every Dart application basically starts at its main method. main top-level function. And if we run it, we find that, yes, it prints this string, and then it called print fields of object with a new point. And what we found is that point had two fields, x and y. And each one of those, in fact, gave us an instance mirror on the value, right? The value 0 that's in there, we're actually getting a mirror on that because the whole mirror system traffics in mirrors, right? It's very important that we do that to preserve those properties. This will work in distributed settings, and we will never be reflecting on something that we don't have an indirection to. So that's kind of very, very basic use of mirrors. You can, as I said, do this in Java. Let's try and do something a little bit more elaborate. If we have time, yeah, we have a few minutes. We're going to construct these library wrappers, which are objects that are going to reflect on a library. They're going to have a library mirror in them, LM. You're going to give them a name of a library. They're going to ask the current mirror system, which is, again, something you get from the mirror library. They're going to ask it for its libraries, which, again, is a map. And they're going to look up this library name in it, and we'll get a mirror for that library back. So that's how this library wrapper is set up. And then what it does is when anyone calls it, invokes a method on this object, since it doesn't have any interesting methods, it's going to go to no such method. And I've got to set it up to print out the name and arguments, but really its real functionality is that it is going to call, depending on whether this is a method, a class, a variable, etc. It's going to use the mirror system to actually extract the value and give us a result back. So we can actually do this here if we uncomment this code. Comment this out so that it's happy. As you can see, the editor is doing its job complaining about stuff, but once we actually save this, it should be happy again. Right, and now we should be able to run this and see what it does. So it's done a whole bunch of things, and we basically gave it a new, we asked this library to, we called point on it, and point is a class. So what we've done is we've actually returned a class wrapper on that class over here. The arguments were point and an empty list of arguments, printed that out. Got an instance of class wrapper. Class wrapper is a similar class that we got up here that does the same thing for classes. Basically, again, obtains a mirror and does a no such method so that you can actually treat the class as an object and invoke its static methods as if they were instance methods. So you can abstract over the class, pass it around, and treat it as a real object. And so when you ask the library for point, it gives you that wrapper. Then you can call static methods of the class or what have you doing that. And a few comments on what we're going to do later. This was basically introspection. Introspection plus no such method, which is one thing you can't do in Java, lets you already do some interesting things. But obviously you want to be able to do things like mutate code on the fly and do fix and continue debugging and all of that. The mirror system should make that relatively easy to do in time. Now the problem is with this stuff is, beyond the fact that we haven't done it yet, is that the web is again such a challenging environment, right? What happens when you minify code, right? What are you going to do when you have a string and you look up a method by string, but that method isn't actually there under that name? Or maybe the tree shaking has actually eliminated it because your basic code never called it. It was only going to be a reflective call based on, say, user input, right? So it's not actually there. Now, you could just say, okay, we use mirrors and all bets are off. We just send you a big download and we don't worry about this, but that's not likely to be what you want. What you actually want is some fine-grained control over this stuff, right? And we have a metadata mechanism that we plan to use for this, so you'll be able to annotate your code, essentially, and say, you know what, this method, even though it's not being called anywhere, please preserve it so that I can use reflective functionality on it. And that will, the deployment tool, whatever it is, Dart2JS or other tools, will look at that annotation information, and that'll influence how it packages the code for you. So it'll preserve that stuff so your reflective calls will work. All this has, is stuff we're planning to do. to let you do the kind of dynamic stuff you want to do, but do it while preserving performance, security, etc. If you want to know more about this stuff, obviously there's, you can go to the academic literature and see this paper on mirrors that I wrote with Dave Unger, who did Self a few years ago. You can read a very short blog post that kind of gives you the essence of this as well. You can also watch a detailed video that a lecture I gave a couple of years back that kind of walks you through all this in great detail and illustrates the real advantages of mirrors in less of a whirlwind fashion. Finally, again, the point of all this is to create a civilized environment, something where you can do real software engineering, build really large apps without jumping through incredible hoops and dealing with the very bizarre set of circumstances that the random evolution of the web has presented us with. And the language is a key part of that because it supports toolability, it supports software engineering, and with a Dart VM, you're actually going to get better performance. And the advantage of a language that works this way is eventually we'll have a much cleaner model for everything through good libraries. We should be able to write stuff that works on the server and communicates via message passing to the client and vice versa through the isolate mechanism, and not care where that server actually is, right? Whether it's a local process or something, not to have to dance through all these orifices, essentially, that the browser provides. So basically, it's all about raising the level of abstraction back to something that's analogous to what native code can do. As far as status, we had our M1 release today. It's all open source. We've been doing open development on this thing for about a year now. Every bug reports, every patch, everything is out there in an open repository and with a mailing list and forums, and is being followed by a core community. And if you want to find out really all the nitty-gritty details, please go to dartlang.org. There you'll find lots of material, some of it much more detailed and much more focused on your typical web programming tasks. And if you have any questions, I'll take them. And if you could go to the microphone, because they want to record all this stuff.
So I have a few questions. One regarding the GWT status versus the Dart in Google. And the second question, where do you use it internal? And the last question, are you going to do any ramp up regarding the library, like something that you get from jQuery or other library out there regarding UI functionality and stuff?
Okay, so that's a lot of questions. So GWT is, as far as I know, alive and well. There's tons of stuff at Google that uses it, so it's still, hasn't been thrown under a bus or anything. On the other hand, we're focused on Dart and doing something that's, in our mind, better. I mean, one of the advantages is that, because we have a VM, we have a great advantage. We don't have to wait for long compiles. Dart2JS is a lot faster anyway, but it's really part of that experience with GWT that is feeding into Dart. As far as libraries, there's a bunch of libraries already. All kinds of people are doing open source stuff. We're focused mainly on core libraries, on basic platform functionality. And you had a question in the middle, but I lost track of it. Yeah, so we do have internal customers. Eventually, I hope you'll see some of those results externally, right? But in general, at Google, we don't comment on that sort of thing. But yeah, we do have people using it internally.
Hi. I know there is a way to call JavaScript from Dart, but I was wondering if there was possible to do the opposite, call Dart from JavaScript. The idea is to be able to implement something in Dart, but still provide an API in JavaScript so that external
right. So what you want to take a look is the new mechanism for talking to between them that Vijay has just released. It's part of the M1 release.
Oh.
There is, I think there's an article on the site that describes this. Basically, it's a mechanism for making it easier for the two to talk to, right? There's some overhead in talking to them because, again, potentially these could be on different VMs, and we want to make sure that works. But it's not nearly as painful as it was, say, a few months ago.
would that be supported by Dart to JS?
Absolutely.
Perfect.
That's very much the point, yeah.
I just had a question about the Dart VM that obviously doesn't exist in browsers just yet, but I was wondering, does it have an intermediate form? Obviously you take Dart and you transpile it to JavaScript. Is it something that in the future possibly that VM would be a common substrate that people could compile to, or is it just Dart as text?
It doesn't really have an intermediate form. It works very much like, say, V8 does. It takes source code and does its thing with it. There is this notion of snapshots, which are a way of allowing quick startup that works on the VM, and that relies essentially on leveraging some of its internal representation. Essentially, it saves you the parsing time. It has a tokenized stream and stuff like that, but nothing that is yet a public standard intermediate representation. It's way too early to speculate on that. If the snapshots really caught on, you could imagine maybe doing something about that, but right now, no.
Okay, thank you.
All right, I guess that's it. Thank you very much.